Hello everyone. So this class for Monday we are going to start with an example problem, and in this example problem I kind of want to show you how to deal with work done and also energy conservation equations. So hopefully, and after that you can work on the clicker questions. There's another example problem. I also I'll post some links for that too. So also check that one too, to kind of get familiar with the process that we follow in chapter 7. So the example problem is on page 211, and it's about a winch which is used to lift an object initially at rest and has a mass of 75 kilograms. The object is lifted 10 meters by the winch's cable. The acceleration of the object during the lift is 1.5 meters per second squared. And since it is lifted upward, we know that the acceleration is also upward. We will determine the work done by the force the winch exerts on the object, and we'll find the work done by the weight of the object and also determine the object's velocity after it has been lifted 10 meters using two different methods. Okay, so several things that we need to do. So the given and find are already shown. I have added a couple other things. So first of all, you can see that there's the position, you need to find the velocity and such. So since it looks like we might need to use the position equation, so you have to kind of show where the origin is. Yes, you have an x and y axis, but you don't have the origin, so you have to show that. The assumptions are we ignore air resistance, there's no drag, and since the forces are constant, acceleration is constant. You can add more stuff, and I usually use more stuff in the, like when I apply energy conservation. I'm going to think about if there's a molecular level change, is there elevation change, is the speed changing, what are the forces, and also if there's heat added or removed from the system. So the plan is, since we are trying to find work, we're going to use the work definition F dot D for both forces. And for part A, it's asking for work done by the force exerted on the object. And hopefully that you can see that since it's winch, it's connected to like a rope or cable. That force is the tension force. So we are looking for the work done by the tension force for part A. Again, for part B, we will also use the work definition, but for the speed of the object, we can, since we are in the energy chapter, let's use energy conservation. And for part D, we will use another method, and that method is usually using the second law and also the constant acceleration equation. So you can give more details, okay? I'm not giving too much, I just kind of write some of the equations. Estimations. So we are estimating the work done by the tension force. To be able to do that, we know that we just kind of roughly multiply the force and the displacement, right? And I just want to show that. So the acceleration was this way, and also the displacement, so check that direction. So when I think about the work done, I think about the displacement and the tension directions. They're both upward, and I'm thinking about cosine function because the work done is FD cosine theta, right? If you write it in the scalar form, that theta is the angle between T and D. Since they point the same direction, theta is going to be 0. So when I estimate, once I get that, it turns out it's just the multiplication of T and D. The problem is I don't know T. So I have mass. I can use that to estimate the weight force. And let's just use roughly 10 meters per second squared as the gravitational acceleration. So that would give us a weight force of 750 newtons. But then if that is roughly what the weight force is, what is tension? Is it the same as the weight force? Is it more or less? And looking at the acceleration, you should figure that out, right? Because you need to have a net force along the acceleration direction. So since acceleration is upward and tension is upward, tension should be greater than the weight force. And if weight force is 750 newtons, then you can, if you want to round it, I would probably make it 1,000 newtons for tension. Again, just so we can get some numbers in order of magnitude. And since that is 1,000 newtons almost, and D is 10 meters, you're going to multiply them to get the weight force, the work done by tension. That's why I have 10 kilojoules. So 1,000 times 10 is 10,000, right? So that's the approximated number, and it's going to be positive because D and T are both pointing the same direction. Cosine theta is going to give you positive value, and it's basically, in this case, it's positive 1. For part B, it's the weight force, the work done by the weight force. First thing I see is weight force and displacements are opposite to each other, so that means the angle between them is 180 degrees. Cosine 180 is going to be negative. So knowing that it's negative, also I can compare the magnitudes. Since weight force is about 750 newtons, so it's less than the tension force, the work done by the weight force should be less in terms of tension work done. In magnitude though, but it is negative as well. Okay, so you can also estimate that. For part C and D, we are looking for the velocity. For 10 meters, again, the acceleration is much less than gravitational acceleration. I don't expect it to be much more than a few meters per second. So if it was a free fall versus it's much less, and it's also speeding up upward, not downward, but within 10 meters, it shouldn't reach very high velocity, right? So hopefully you can estimate those. And next we are going to solve the problem, but that's kind of how you set it up. And I'm going to stop here and continue in the next video.